Bom, opa, agora que começou aqui, agora eu me atrapalhei aqui. As janelas, meu Jesus, o que aconteceu? Pessoal, eu vou tentar aqui, então, falar um pouquinho para vocês, então, do trabalhinho que a gente começou a fazer. A gente tem... I'm sorry. So, good afternoon, everyone. My name is Cleber Mendonca, and today I will present some results on the fabrication of metasurfaces using laser-induced forward transfer on silk fibroin. So the idea of metasurfaces is actually to create a surface which is composed of a planar metamaterial in which we can tailor the optical properties of such material by changing the geometry and the index of refraction of the materials. So in general, it is made out of one or a few layers of periodic structures. It in general presents properties that you don't find in nature, and it allows tailoring the optical properties. Some of the applications that people are thinking of using metasurfaces are in thin mirrors, enhancing the optical field, tuning resonances of materials, and suppressing reflections in specific wavelengths. So in general, the way we fabricate metamaterials or metasurfaces is by using the traditional photolithography methods, such as optical lithography, electron beam lithography, scanning probe lithography, and non-imprint lithography. So those are methods that everyone knows how to use very well nowadays. However, depending on some features you want to produce, such methods, they are not enough, because most of them are mostly dedicated to a given group of materials. One option in order to enhance the number of possibilities for producing metamaterials is by using direct laser writing. So the idea here is using femtosecond lasers, which are focused on a given material, to change the material properties, or somehow to produce the periodic structures with that index of refraction you have in mind, to fabricate metasurfaces. And the good idea about using direct laser writing is that you can use for a big variety of different materials. In our group in São Carlos, in the last few years, we have been using a femtosecond laser micromachining or direct laser writing to fabricate, for instance, surfaces in which we can control the wettability of that surface. We have been using we have demonstrated the fabrication of waveguides, three-dimensional microstructures made out of polymers, volumetric waveguides, three-dimensional microstructures for several other applications, and also localized crystallization of materials. Therefore, as we can see here, it can be used for different materials, from crystals to glasses and to organic materials. So it's a very broad way of processing different materials. For fabricating those metasurfaces, we are looking for, in this work, we have used laser-induced forward transfer. So basically, the idea is focusing the laser beam here in the donor substrate, and then the material is ejected to the receiver substrate. And then, of course, by moving the laser beam here on the donor substrate, we can create different profiles on the substrate, on the receiver substrate. This technique, in this specific case here, this technique will be performed using femtosecond lasers, in such a way that we can increase the resolution, and at the same time, we doesn't damage the material upon transferring. which might be a problem depending on the type of laser you can use. So it's a very flexible way of producing patterns, and also in general doesn't damage the material. So you transfer the material and it keeps its initial properties or its original properties. Just to give here an example of applications of the lift. So there's a thermocouple fabricated by lift. Here it's a micro bridge between two different areas of a given circuit, for instance, this side and the other one. Here you can see some fold connectors, but so those are more, let's say, traditional methods or traditional applications of lift. And also people have been using lift to transfer or to print cells, as you can see here in those two figures. So in this case, those cells, they have been transferred by using lift. Okay, what are the advantages of lift in our specific case? So because we use femtosecond, it improves the resolution of the transferred materials or of the transfer structures because of the nonlinear nature of the interaction, and at the same time, it minimizes the damage to the material properties by reducing some thermal effects. So it looks like a very interesting approach for producing metamaterials. Therefore, the goal of this work here is to demonstrate the use of femtosecond lift to fabricate dielectric microstructures or microsurfaces using silk fibroin. And so why silk fibroin? Because it's a natural polymer, and so it's very flexible because it offers several opportunities for the processing in different ways. It allows functionalization of the materials. You can also do some biological integration, and it's also a material that presents also very good optical properties. It's very transparent and also mechanical properties. Here's the setup for our femtosecond laser lift. So basically the femtosecond laser comes this way. We focus the laser here in the substrate containing the fibroin film, and then by scanning the beam or by moving the donor substrate, we can fabricate different structures or different periodicities on the substrate, on the final substrate. So here's some studies we performed on the silk fibroin deposition. So as you can see, depending on the energy, we have those small circles. So those are SEM, scanning electron microscopy images of the fabricated structures. So as you can see, depending on the energy, we are able to increase the diameters of the fabricated structures or the fabricated ellipsoids. And the threshold energy depends, of course, a little bit only on the scanning velocity, but it's on the order of 27, 28 nanojoules. So here are some atomic force micrographies of those structures which were deposited. So as you can see, they are very smooth surfaces. They are basically circular in the plane or on the plane, but on the z-axis it has this kind of profile. I have to show here. I was pointing there. I'm sorry, guys. So in here you see the profiles. So as you can see, it's not really a circle. So it's not really a sphere or an hemisphere, because it's usually it's higher in the z direction than in the xy plane. Okay, those are, so as you can see here, it's, or the other way around, I'm sorry. It's longer in the XY plane than in the Z direction. So as you can see here, it's, let's say 8 microns across, but it's only 1.5 microns high. So this is the kind of structures we have. So here's just to show that we are actually able to fabricate periodic structures. Those are again SEM microscopies. SEM images of the microstructures. That's a image in angle. So as you can see, we have some periodicity, and that's the kind of structure that we would like to propose as a metasurface. So that's the way we actually fabricate the metasurface using using the lift approach. So before we actually try to do some measurement on the fabricated metasurface, we decided to do some modeling to see which kind of property we would be able to observe. So first of all, by analyzing the image as the one here in the background, we determined the average radius, and we actually determined the network of our structure, which is actually anisotropic. So what you can see here, so that's the index of refraction. So those are some finite elements results in which we present here the reflectance as a function of the wavelength, so for different diameters. So in our case, as you can see here, the radius is 1.6, so the diameter is 3.2. So as you can see, 3.2 is in this line here. So as you can see, we have a decrease in the reflection, which goes to a smaller value at about 4 microns, okay? So if now take a look in that profile, so here I'm actually plotting now this profile. So of course, as you can see, depending on the diameter, it changes a little bit, but not much. So the behavior is about the same for all the diameters from 2.8 to 3.2 micrometers. So the surface we fabricated, it actually has a reflectance which is smaller than the Fresnel reflection. So here it would be the Fresnel reflection for the glass. And then here is the reflection that we actually calculated for the structure we're looking for. And then at 4 microns around here, what we can see is that the reflection, it's about half, okay? So if the Fresnel reflection is 4%, at 4 microns, this metasurface we fabricated should have a reflectance much smaller, or at least of 0.5%. Okay, that doesn't sound very good, right? Maybe you can say, okay, that's not too impressive because, I mean, from beginning, the microstructure does, the glass itself doesn't have a high reflectance, so it's already 4%. So we are dropping from 4% to only 0.5%. However, that's just a proof of principle that we can use lift as a way to fabricate metasurfaces. And then we also did some modeling now, considering that we can actually do exactly the same thing, fabricating the microstructures using lift for n equal to 3. So as you can see here, in this case, so if now the refractive index of the material is 3, let's say here at about 6.2 microns, you do have some enhancement or some higher peak for the reflectance. So here again, I show this profile, right? So the spectrum of the reflectance for n equals to 3. So as you can see now, at 4, the reflectance goes to 0, and at about 6 microns, the reflectance goes to 1. So that shows that we, in fact, can use lift to produce a structure in which we have no reflection, or in which we have a higher reflection at a given specific wavelength. Okay, so what we actually measured so far. So that's not really the reflectance of the material, that's like a relative reflection. Of course, we are doing that in the infrared, so it's not that easy. Anyways, so by now, the only feature that we actually observe that we can actually compare with the modeling we got is, so here will be the reflection for the glass, or the relative reflection for the glass, and that's the relative reflection for the metasurface. It doesn't really look like exactly the modeling. We are still trying to understand what's going on with this experimental data, but for sure it decreases. So for sure now we have a material in which the index, the reflectance is smaller than the reflection of the glass. And the other thing is that all the modeling was carried out at 0 degrees at normal incidence, but this data was taken at 45 degrees. So now we are trying to do the calculation at 45 degrees to see what's going on. So the last thing I would like to show you is how does it look like when you look by naked eyes on this structure here. So this video, so that's our metasurface. So as you can see, depending on the angle, so that's just with white light incidence. So depending on the angle, you see different colors. So that's the iridescence of our structures. So here I'm taking some pictures so you can see better. So you have like a violet color, blue, green, and here something which is green-yellow color depending on the angle. So therefore, it does present some iridescence. So the reflectance does depend on the angle, and that might be an indication of some photonic band gap structures. And right now we are trying to calculate the band gap of these structures to see if it agrees with whatever we are observing here. So with that, I would like to thank you for your attention and to the funding agencies for their support.
Você está mutado, Cleber.
Apertei o botão errado, saí da chamada.